we introduced posterior distillation sampling. Posterior distillation sampling, PDS in short, is a novel optimization method that can edit diverse visual content using 2D diffusion priors. For example, given a 3D scene represented by nerve, PDS can produce high-quality editing results. Beyond appearance changes, PDS is the first to achieve large geometric changes in 3D scenes. For example, PDS can make a man raise his arms in 3D scenes. Also, it can even add new objects to 3D scenes, such as adding hot air balloons to an outdoor scene. The editing capabilities of PDS are not limited to specific representations. Besides nerve editing, PDS can also edit 3D Gaussian splats and SVGs. In other words, PDS can perform editing on various parameterized images regardless of representation. Score distillation sampling, SDS in short, is the first optimization approach. It leverages a pre-trained 2D diffusion model to process visual content beyond 2D images. However, SDS was originally designed for generation. For editing, delta denoising score has shown superior performance in 2D image editing. Despite the impressive results in 2D images, DDS fails in 3D scene editing, producing outputs that lose the original identity of the input 3D scene. To achieve superior editing, we propose posterior distillation sampling. To compare these optimization methods, we conduct toy editing experiments. We consider a 2D distribution separated by two marginers, each of which is colored by red and blue respectively. Given this 2D distribution, we train a diffusion model conditioned by class labels Y. Then our goal is to move points sampled from the red distribution to the blue one using different optimizations with the pre-trained diffusion model. In the case of SDS, all different points converge to the same point at the end, which indicates a mode collapsing issue happens in SDS. DDS significantly displaces points from their initial positions, which means that it loses the original identity in editing setups. On the other hand, PDS is the only one that makes minimal changes to move points to the target distribution. It demonstrates that PDS balances the conformity to the target attribute with preserving the original identity, which are two key aspects of editing. PDS leverages so-called stochastic latent, which is computed from the reverse process of DDPM. Here, the equation represents one step of the reverse process, sampling xt-1 from xt. Given a noise latent xt, an input text prompt y, and a pre-trained diffusion model, we estimate the mean of the posterior distribution and finally sample xt-1 by adding random Gaussian noise to this mean value. From this reverse process equation, we can compute stochastic latent as follows. Here, xt-1 and xt are sampled from an input image x0 via the fourth process of diffusion models. Given a pair of an image and its corresponding text prompt, in PDS, we first compute the stochastic latents for both the source and the target. Then the optimization function of PDS matches these two latents. Expanding this equation reveals that there are two terms in PDS, one for identity preservation and the other for text-guided editing. Also, we demonstrate that this process of matching the stochastic latents resembles aligning the reverse processes of the source and the target. Thus, it ensures that the target image does not significantly deviate from the original source image. Here are more nerve editing results achieved by PDS. And this is additional SVG editing results achieved by PDS. For more detailed information, please refer to our paper or attend our poster session on Thursday morning. Thank you.